In this example, we're dealing with an object that is 1.2 meters above the surface of the Earth. We also are given the fact that the radius of the Earth is 6.38 times 10 to the 6 meters. We know the mass of the object is 1 kilogram. We know the mass of the Earth is 5.98 times 10 to the 24 kilograms. And we also know the gravitational constant, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And the question is, what's the gravitational force between the Earth and the object? Well, we know an equation for gravitational force. The gravitational force is the gravitational constant, capital G, times the mass of one object times the mass of the other object, divided by the distance between them squared. So really all we have to do is plug in the numbers. Gravitational force equals capital G, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, times the mass of one object, 1.0 kilograms, times the mass of the other object, the mass of the Earth, 5.98 times 10 to the 24 kilograms, divided by r. But what is r? That's the main point of this example. R is defined as the distance between the centers of the two things in question. Here we have the Earth. The distance from the center of the Earth to the surface of the Earth is 6.38 times 10 to the 6 meters. Then the distance from the surface of the Earth to the object is an additional 1.2 meters. So, the total distance between the centers of both the Earth and the object is 6.38 times 10 to the 6 meters plus 1.2 meters. That's r. Now look at these two numbers we're going to add together to make r. 6.38 times 10 to the 6th and 1.2. Realize we have to deal with significant figures here, and we're adding, so we look at decimal place. 6.38 times 10 to the 6th has its last significant figure in the 0.01 times 10 to the 6th decimal place. That's 10 to the 4th. So that's the 10,000s decimal place. 1.2 has its last significant figure in the tenths place. So when we add these two together, we can only report to the 10,000s place. Well, to the 10,000s place, 1.2 doesn't even exist. So 6.38 times 10 to the 6th plus 1.2 is really just 6.38 times 10 to the 6th. In other words, since the distance between the surface of the Earth and the object is so small compared to the radius of the Earth itself, we can ignore it. That turns out to be a general conclusion. Most of the heights that we deal with are so small when compared to the radius of the Earth that when adding them to the radius of the Earth to get r, they just don't count, so we simply ignore them. That's why we assume that the gravitational force is constant near the Earth's surface. What does near mean? Well, near just means any height that is small compared to the radius of the Earth. Please realize, however, that that only works if the height is small compared to the radius of the Earth. Once we start getting really high, up in the mountains and in a plain and that kind of stuff, the height is no longer negligible compared to the radius of the Earth, and we do have to include it. But in most situations that we're familiar with, the height is so small compared to the radius of the Earth, we simply ignore it, and we assume that the gravitational force is constant near the surface of the Earth. Alright, now we can finish the problem. Notice that meters squared cancel and kilograms squared cancel, leaving us with newtons. That's good because force has a unit of newtons. When we work out all the numbers, we find out that the gravitational force between the object and the Earth is 9.8 newtons. Now remember, since the height of the object is very small compared to the radius of the Earth, basically any 1.0 kilogram object anywhere near the Earth's surface will experience a gravitational force of 9.8 newtons.